Hello, welcome to the first lecture of week 4. What we'll be doing in this week, and again we'll continue to the next week as well, we'll learn different methods to determine deflection in statically determinate beams and frames. So our topic is for week 4 and week 5, analysis of statically determinate structures, deflection of statically determinate beams and frames. In this week, we learn different methods to determine deflection for beams, and the next week we'll extend that method, some of the method to frame, and also see principal virtual work to determine the deflection. If you remember, principal virtual work was introduced in the last week. Okay, now as far as beam is concerned, we learn 3 methods here, but if you we'll introduce those 3 methods as we move on. But there is a common thread between all these 3 methods, and the common thread is equation for elastic curve for beam. What we'll do today is we'll derive the equation for elastic curve. What is elastic curve? How is the equation? We derive that equation today, and then next classes onwards we'll see the application of this equation in several forms, different way, which gives actually different methods for determining deflection. Okay, now let us start with this. You see, take a beam. It's for demonstration purpose. It is we are considering simply supported beam subjected to UDL, but the concept that we develop, the equation that we develop, that is applicable to any support condition. Now take consider a beam which is subject to uniformly distributed load intensity Q. What are the length of the beam is L, cross section of the beam is A, second moment of area I believe that you are familiar with second moment of area, you have learnt it in your mechanics course, and modulus of elasticity or Young's modulus of the material is E. Now so this is the physical process. Now this deflects like this, right? Now what we do is, this is then idealization of this physical process, where the beam is idealized as line, okay, because this length is very small as compared to A. Now what do we, now if we take any section any section Mn at a distance A, at a distance x from A, then this deflection of this beam is y. Now what we want is we want an equation that relates the forces acting on this structure, deflection, material, and geometric property. Means we want the force, the deflection as a function of x, because as we can see the deflection changes with x, which is obvious. If we change q, deflection will also change. If we increase q, deflection will be more. The Young's modulus is the material strength has influence on the deflection, and then of course the geometry of the section also has some influence on this section. Okay. Now what we want is this, we want to derive an equation which gives you that relation. Now if you remember, in the first lecture we said the process we follow is a physical process, then idealization, then derivation of the equation representing this idealized physical system through some equation, and finally solving those equations. What we'll do today is we'll derive this equation, and then how to solve this equation in a what form, that we'll see in the subsequent classes. Okay. Now any model is based on certain assumptions. What are the assumptions that we have for the model that we are going to develop is this. The first is the material obeys Hooke's law. You are familiar with Hooke's law. What it says is, just quickly, that implication of Hooke's law: if you have a spring which is subjected to a force P and undergoes deformation X, and the spring constant, the spring stiffness is K, then we say that then P can be determined from Kx. When K is the deflection, P is applied deformation, applied load. Now, it says that the applied load and the deformation is linearly related, and the slope of this relation gives you the spring stiffness. And if you have to write it in the stress and strain form, then this is the stress strain relation of any typical stress strain relation of any material. It is initially it is linear elastic, it obeys Hooke's law, and then it becomes non-linear, it goes into inelastic region. Now, slope of this elastic region will give you the stiffness. At the point when it changes from elastic to plastic is called yield point. Okay. Now, assumption is another important part you can note is here it is elasticity does not always mean that the relation has to be linear. There is nonlinear elasticity as well, but that you can Google or look into different books what nonlinear elasticity exactly means. Now, this assumption is the theory, the model that we are going to develop, that is applicable when the material is in this region, this elastic region. If the material goes below outside this region, then this equation is not applicable. Okay. Okay. Then the second assumption is curvature is small. This is the curvature of the beam. If this is the deflected shape and rho is the radius of curvature, and the curvature gives you 1 by rho, and it is assumed that this is very small. Now, and the third assumption is, it is a very important assumption. These two assumptions are in some way they are related. Third assumption is very important assumption. What it says, please note, any cross section originally plane and normal to the neutral axis remains plane and normal to the neutral axis during the deformation. Let us see what it exactly means. Now, suppose this is a beam in undeformed configuration, and if we apply some load, say some moment, then it goes deformed configuration like this. Now, this is the centroidal axis or the neutral axis. Now, if we take a section, suppose two sections here and here, which is initially normal to the neutral axis. So, this angle is 90 degree, and this is the deflected shape of the neutral axis. Then also, and this section becomes this in deformed configuration, and this, if this is 90 degree initially, this 90 degree that angle preserves. So, it remains normal to the neutral axis at this point. Okay. Now, you see this another implication of this assumption is, suppose this is a beam and it is subjected to some load and it bends like this. Now, here are two deformed configurations are shown. One is with bold red line and another one is dotted green line. Now, bold red line probably the actual deformation that the beam may undergo, but what this line is the blue dot lines, which is the cross section which is normal to the neutral axis. Now, what happens when it undergoes deformation in deformed configuration? It was initially undeformed configuration, this line is a plane, but in deformed configuration the deformation which is shown in red line, this plane does not remain plane, right. But our assumption is the green dotted line, that if it is plane, it remains plane. So, there are two important things here. One is a section which is plane, it remains planes. This is first thing, and the second is, if the section is normal to the neutral axis in undeformed configuration, it remains normal to the neutral axis even in deformed configuration. Now, this is very important. The reason is, and my experience says, whenever I ask student to say the assumption, the student says that plane section remain plane. Plane section remain plane, it is true, but this is not a complete statement. This is an incomplete statement. What we have to say is the plane section remain plane, of course, but originally, if undeformed configuration, if it is normal to the neutral axis, then it remains normal to the neutral axis even in deformed configuration. Okay. Now, so these are the assumptions. As I said earlier, assumptions are a limitation of any model. We will see some of the cases where these assumptions are not valid, and therefore, we may need a different theory to represent those physical processes. Okay, but for the for our purpose, this assumption is reasonably enough, because if we look it from civil engineering point of view, one of the if you remember, there are two criteria for design, mainly two criteria. One criteria is the safety criteria, another one is serviceability criteria. Safety criteria says that the internal forces in members, they should not cross, they should not be more than the maximum capacity of those members. This is a safety criteria. Serviceability, one of the serviceability criteria is deflection should not be very high. Now, that criteria is design criteria is very consistent with this assumption, because anyway at the time of design we impose this restriction that your deflection should not be very large. Therefore, since the deflection should not be very large, we are not going to allow deflection to be more. Therefore, on those cases these assumptions are applicable. But remember, beam is just not beam doesn't belong to only civil engineering. Beam is a very important structural idealization. It has application in various fields. The concept of beam has application in various fields. So there are cases, there are situations when the idealization is beam, but that beam, the behavior of that beam is not consistent with these assumptions, and in those cases we need to go for different theory. But for us, this is absolutely fine. Okay, now let us derive. Once the assumptions are made, let us go with the derivations. Okay, now consider this is the idealized model. Now, what we need to find out? We need to find out y as a function of different parameters, right? Okay, this is our objective. Okay, now you see the radius of curvature you can determine. This is a very standard expression. If y is a function of x, then the radius of curvature, any curve, can be represented by this. Okay, this is a very standard result. But again, we assume our deflection is small. That's what our assumption. We discussed the assumptions. Deflection is very small, and if the deflection is very small, then this radius of curvature, this expression can be idealized as deflection and slope are very small. So this part gives you the slope. This is very small and deflection is very small. So this radius of curvature can be approximated as this. Okay, you put a star mark here, this absolute value. We will discuss what will be the sign of this radius curvature and as we move. Okay, so now radius of curvature is this. Curvature is this. Okay, okay. Now consider this is a beam which is subjected to pure bending. Okay, I mean there is no shear force, only bending moment. This is the neutral axis, the blue line that you can see. And this portion of the we take some lines. These are you assume these beams are essentially a collection of certain fibers. It's a collection of certain fibers across the depth. So we take some fibers above the neutral axis, and then some fibers along the below the neutral axis. And the fibers are or the planes are in this direction along the length of the beam. Now, if it undergoes deforming, this is undeformed configuration and this is the deformed configuration. Okay, this is deformed configuration. Now, you know this, but still just to look at in a proper perspective, in a better in order to appreciate the theory in a better way, we are again discussing all these things. Now, you see, for this kind of bending, for the sign convention that we follow, that sagging moment is positive and hogging is negative, above the neutral axis, all these planes or all these fibers are under compression. Okay, so their length decreases, whereas all these fibers below the neutral axis, they are under tension. This is not shorter, this is longer. Okay, there is a typo here, please note, this should be longer. Okay, so this is in deformed configuration. Now what happens? This is neutral axis. Okay, now we take two sections, a section Mn and PQ, or we take a small element in this beam, Mn, Q dash and P dash, and correspondingly that element becomes this. Okay, our first assumption, our assumption was these are normal to the neutral axis, these are, it remains plane, and again it normal to the neutral axis. And suppose the P dash Q dash is what is undeformed configuration. In deformed configuration, suppose this is PQ, and undeformed, and P dash Q, it is undeformed positions as shown in dotted lines. Okay, so P dash Q dash now become PQ in deformed configuration. Okay, now suppose this length, the distance between these two plane A and 2 points A and B is dx, delta x. Okay, or dx. Now what we do, take this part, zoom this part and draw it here. And what are the things we have? This is the neutral axis, this is the this view in the larger view of this part. Okay, this is the neutral axis, Now top fiber which is under compression and bottom fiber which is under tension. The top fiber the length decreases and the bottom fiber length increases, or for that matter all the fibers below the neutral axis, they are under, their length increases, and the above the neutral axis they decreases. M, N and P dash Q dash are these two planes, and P dash Q dash they take a form PQ. Okay. Now once they take a form PQ, suppose this angle between this M and N and PQ is theta. Okay, or it is d theta, that is better way of expressing it, this is d theta. This is, therefore this angle is also d theta. Okay. Now distance, this is the undeformed position of undeformed configuration, position of PQ in undeformed configuration, and their initial distance was dx. So this distance is dx. This is A and this is B. Okay, and suppose this rho is the radius of curvature of the neutral axis. Okay, now we take a fiber or a fiber at a distance y from the neutral axis. Okay. Now since this fiber is below the neutral axis, what happens is the initial length of the fiber was CD dash, this length which is delta x, which is dx. Now this CD dash now take a form CD. So CD dash now elongated to CD, and the elongation of CD dash is d dash. Okay. So CD dash is under tension, and because of this tension the elongation takes place is d dash. Okay. Now so this is d theta. Okay. Now if this is d theta and this is dx and rho is the radius of curvature, so naturally we can write dx is equal to rho d theta, and which gives you d theta dx is equal to 1 by rho. Now 1 by rho is the curvature. Now as I said, the fiber CD dash is elongated to CD, which is essentially CD dash plus CD dash plus d dash d, and therefore the d dash d is again can be written as, since this angle is d theta, d dash d can be written as y into d theta. Okay. Now then what is the longitudinal strain in this fiber? Longitudinal strain, this is under tension, and the longitudinal strain in the fiber will be a change in length divided by the original length. The change in length is d dash and original length is dx. So this is the longitudinal strain, and d dash we just determine y d theta, and this become y d theta, and from this from 1 we can write that elongation is equal to y by rho. So one important observation here is, as y is equal to, when y is equal to 0, then epsilon x is equal to 0. It says that at the neutral axis your strain is 0, and y is equal to positive, if epsilon x is positive, it is tension, y upward direction negative, that's what our sign in this case. It becomes negative, so it is under compression, and between top fiber to bottom fiber, how it depends, how the strain depends on y, the strain depends linearly on y. So the variation of the strain will be linear, and the strain at the neutral axis is 0. That's why it is called neutral axis. It remains neutral when the beam undergoes deformation. Okay. Now, longitudinal strain in fiber is this. What would be the longitudinal stress in fiber? Longitudinal stress in fiber is this. This is Hooke's law, that stress is equal to Young's modulus into strain. So, if we epsilon x, if we substitute, then stress is equal to this. Again, the same observation for stress. Stress is linearly varying across the depth, and at y is equal to 0 at the neutral axis, stress is 0. It remains neutral. Okay. Now, longitudinal strain and longitudinal stress, we have longitudinal stress is this. Okay. Now, consider this is the beam, and suppose this is the cross section of the beam, right, and this is the distribution of stress which is varying linearly across the depth. At the neutral axis it is 0. Sigma c is the maximum compression at the topmost fiber, sigma t is the maximum tension at the bottommost fiber. This is x direction, and downward y for calculation of deflection. If deflection is downward, we say that is positive. It is consistent with our sign convention in moment, because we say the sagging moment is positive. Sagging moment means which causes sagging in the beam. Sagging in the beam means it is deflected, it deflects downward. That's why when it deflects downward, the deflection is considered as positive. Okay. Now, sigma x is this. Now, this sigma x will the body is in equilibrium, right? When the body is in equilibrium, then it should satisfy certain equilibrium conditions. Summation of fx is equal to 0, summation of fy, and summation of moments is equal to 0. Summation of fx is equal to 0 says that total compression will be equal to total tension. If you say it will, you can verify this. Now, and then what is the summation of moment? Summation of moment is we have a sagging moment m here, and the induced stresses are sigma, this sigma. So, whatever stresses, whatever moment generated due to this stress, that should be the moment at this section. Okay. So, how to calculate that moment? Moment will be, if we take any section, small section delta A, then what will be the force in this section delta A? Force will be delta x into dA. dA is the cross section. This will be the force. And what will be the moment of that force? Moment, this cross section is at a distance y from the neutral axis. The force will be y into this force, and if we that will be the moment due to force on this area delta A. If you integrate over the entire area, that will give the total moment. Sometimes that's why these moments here, for they are also called stress resultant, because they are resulted due to the induced these stresses. So, this will be the moment, right. Now, if we substitute the expression for sigma x from this equation, then this gives you E by rho y square dA. Now, you are familiar with this term, integration over area y square dA. This term is called second moment of area. Okay. In this case, it is the second moment of area about this axis. Okay. So, generally second moment of area is represented by I. So, it becomes that if we substitute, if we replace integration of y square dA by I, and then this equation becomes 1 by rho is equal to m by EI. And okay, and 1 by rho we already know, 1 by rho is equal to this for small deflection and small slope. 1 by rho, the curvature can be approximated at this. Now, if we substitute this in this equation, finally we get d2y dx is equal to this. Okay. Now, this is the relation between but still it is not the final form. We will see the final form. So, we get m by EI is equal to absolute value of d2y dx2. Okay. Now, let us see what would be the sign of this. Okay. Now, this is our deflected shape. Now, how we define the sign of curvature? For instance, this line show you different curvature. In this kind of, if the curve is like this, this is the curvature is positive. If the curve is like this, the curvature is negative. And if it is a straight line, then curvature is 0. Now, we assumed when moment is positive, then your deflected shape is this, right? So, when moment is positive, deflected shape is this, means curvature is negative. So, moment is positive means curvature is negative, and similarly if you take hogging moment hogging moment will cause this kind of deflection, which is positive curvature, and hogging moment is negative moment. So when the moment is negative, curvature is again positive, right? Now what happens, therefore see, moment and curvature, they are always in opposite sign. So if we know that if m is positive, they are in opposite sign, so this can be written as this, the sign of this will be minus of this. Okay, this is a very well known equation. This is called Euler-Bernoulli beam equation. Okay, now there are other forms of same equation as well. Let us derive those equation. Suppose consider this is the small segment of the beam, and which is subjected to sagging moment here m at A, and then the moment is continuously changing. So at B, suppose the moment is m plus dm. Similarly, at A shear force is V, and at B shear force is V plus dV. It is continuously changing. Now this is the free body diagram of any segment in a beam. Apply the equilibrium conditions on this free body diagram. Summation of ma is equal to 0. If we take summation of moment about A is equal to 0, then it gives you this moment which is clockwise, then anti-clockwise m plus dmm minus, then this force will not contribute any moment because okay, and then this force will contribute is V plus dV into dx. In this equation, you consider this is under pure bend, this is under bending only. So this, there is no force like this. Okay, so if we substitute this now what happens is, see, dV is very small quantity and dx is also very small quantity. So even when dV is multiplied with dx, then it becomes even smaller, and in that case we can neglect it. And if we neglect it, then this becomes only non-zero part becomes this, and this gives you V is equal to dm dx. And similarly, if you apply Fy is equal to 0, then if we apply Fy is equal to 0, and actually instead of taking moment about A, better you take moment about the midpoint. Okay, then probably it is better, because if you take moment about midpoint, the contribution of this force, contribution of this will go, and then you can arrive at this expression. Take Fy is equal to 0, and this is your all the forces in Fy direction, and this gives you Q is equal to minus dV dx. It is just the brief review of the equation of elastic curve. You might have derive this expression in strength of material course or mechanics course. Now this is very important. If you remember, when we are drawing bending moment and shear force diagram, we observe that if the bending moment is always one order higher than the shear force, and this expression explains that. Okay, now quickly final derivation. These are the expression just now we derived, and this is the expression that also we derived. Now substitute this into this equation, we get this, and then substitute this into this equation, we get this, and again substitute this into this equation, we get this. Now these are the differential equation of elastic line for beam or differential equation for elastic curve. Now depending on the situation, so these equations are essentially the mathematical model which gives you which represent the deflection of a beam subjected to transverse loading. Now any form can be used, and which form to be used, that again depends on what information you have about the problem. Okay, now you see, so what we do is next class we'll use these equations to find out deflection for different beams. But before we stop today, one important point, see, for any theory, assumptions are essentially limitations. Okay, let us see what are the limitations. This theory is based on certain assumptions, and many cases those assumptions are not applicable, and there these Euler-Bernoulli beam equation cannot be applied. We need to go for some other beam theory, which can take care of the which can release those assumptions in Euler Bernoulli expression. Now you will learn those different theory in different subjects, but the idea that what I am going to show you just one case where these assumptions may not be valid. Okay, suppose this is a representative figure. Okay, suppose you have a pipe network like this, okay, and the water flows through this pipe with very high speed, for instance. Okay, now what happens, for some reason, if a pipe breaks, suppose you consider this segment, if a pipe breaks here, then what happens? Yes, if this segment is this segment, okay, this segment. Now if the pipe breaks here, then fluid flows through this pipe, and if it breaks, then fluid will come out from this pipe. Now when fluid comes out from this pipe, then it will exert an equivalent force, that as per Newton's third law, it will exert a force on this. So this can be treated as a beam which is subjected to a force by this water jet coming from this, the reaction from the water jet coming from this fluid. So this is the problem, and this idealization of this problem is this. You have this can be treated as a cantilever beam which is subjected to some force like this. Okay. Now depending on the size of the diameter of the pipe, length of the pipe, and how much the speed of the fluid through this pipe, this pipe may undergo severe deformation. For instance, this is one case where if you see the kind of deformation, this is a cantilever beam, right? In any civil engineering structure probably doesn't experience this kind of deformation. But as I said, beam just not only a civil engineering structure, the beam idealization is used in many places. Okay, many places of mechanics. Now many applications of mechanics. Now this is a very severe deformation, as you can see. Now if you zoom this part, if you see the cross sections, if you take cross sections of this at several cross section, the cross section gets distorted like this. So they are not, initially they were plane, but they do not remain plane. Okay, so these is just one example where these assumptions are not valid. You have many such examples where these equations are not valid, these assumptions are not valid, and if you find out, if you come across those situations, you have to work with different theory which takes care of all these physical processes. But for this, all the civil engineering structure generally, these assumptions are valid. So we'll go with these equations. What we'll do next is we'll take few examples and then see how these equations can be used to find out deflection. Generally, three methods we'll study. One is just the directly integrating this differential equation. This is one method, and the second method is moment area method, and third method is conjugate bend method. So next class we'll will find out deflection of the beams by directly integrating the differential equation that we derived today. Thank you.